All right, let's jump right in. Today, we're covering one of the most vital areas in all of medical imaging, and we're drawing from Lecture 07 by Dr. Mohammed Jafar at RadSound. We're talking about quality control and quality assurance in mammography, the systems that make sure everything works perfectly. And honestly, let's just start with this, because it's the most important idea of all. You can know all the theory in the world, but it means absolutely nothing if the machine itself isn't performing flawlessly. And not just once in a while, every single day. So here's our game plan. We're going to start with why the stakes are so ridiculously high in mammo. Then we'll get into the rule book, the IPAM framework. We'll talk about commissioning, which is the absolute gold standard, dive into the routine checks, and then wrap up with the tools you need to get the job done. Okay, first things first. Why is QA in mammography so much more demanding than in, say, chest X-ray or CT? I mean, what makes it so special? Well, the reasons are pretty profound, and they have a massive impact on people's lives. Think about it. We're imaging a huge population of healthy women, so any tiny error can have enormous consequences. The physics is also incredibly sensitive. A tiny drift in the KV, and your image contrast and patient dose can go way off. And we're on a treasure hunt for things that are literally the size of a few grains of salt. All of this, while keeping the dose to a very sensitive organ as low as possible, means the rules have to be incredibly strict. So, to manage all that complexity, you need a seriously robust framework. In the UK, that's IPEM Report 89. Now, let's break down two key terms you're going to hear over and over: QA and QC. And trust me, they are not the same thing. And this is a really crucial point. Quality assurance, or QA, is the whole shebang. It's the big umbrella that covers everything: the people, the training, the protocols, the audits. Quality control, or QC, is just one piece of that puzzle. It's the hands-on technical part where you're actually testing the machine itself. And those QC tests are split into two levels. You've got level A tests. Those are the simple, frequent checks, think daily or weekly, that the radiographers do right there on the front lines. Then you have level B tests. That's when you call in the cavalry, the medical physicist, for the complex, deep dive, annual tests that require some pretty specialized gear. So where does all this begin? Well, it all starts with the single most important event in the life of any imaging machine: commissioning. This is way more than just another test. It is the bedrock of the entire QA program. So what exactly is it? Why does it carry so much weight? It's because commissioning is what sets the baseline. It's this huge, comprehensive set of measurements you take when the machine is brand new, fresh out of the box, and working at its absolute best. Every single QC test you do for the rest of that machine's life gets compared back to these numbers. It is the gold standard. And hey, this isn't a one-and-done deal. You have to do a full commissioning process, not just when it's new, but anytime you move the machine, or if you have to replace a major part like the X-ray cube or the detector. You have to reset that perfect baseline every time. Okay, so once you've set that gold standard, the mission changes. It becomes all about constant vigilance. And that's where routine QC comes in, the daily, monthly, and annual checks designed to make sure that system never, ever drifts away from its peak performance. And this table just lays out how incredibly tight those tolerances are. I mean, look at this. Tube output consistency. If it drifts by 10%, you have to investigate. If it hits 20%, game over. The machine is suspended. The KV has to be accurate to within 5%. And your image quality can't slip by more than 2 little steps on the phantom before you have to take action. Let's just focus on this number for a second, plus or minus 5%. At the low energies we use in mammo, anything more than that isn't just a, that's weird. It's an immediate trigger for an investigation. This is your first warning sign. Now, here is the hard stop. This is the line in the sand. A 20% drift in tube output from that original baseline, that's a suspension-level failure. It means the machine is unfit for clinical use, and it gets taken out of service, period. And when it comes to image quality, look how sensitive this is. A change of just two threshold groups on the contrast detail phantom is enough to trigger a remedial action. It just goes to show how closely we have to monitor the system's ability to see those faint, fuzzy objects. So let's be crystal clear on what these mean. Remedial level is your yellow flag. Something's a little off, we need to figure out why, but we can carefully keep using the machine. Suspension level, that's the red flag. Stop everything. The equipment is not safe, it's not effective, and it cannot be used on a single patient until it's fixed. All right, so what are the tools of the trade? Let's wrap up by looking at the essential gear we use for these tests, and some special things we have to think about for newer tech like tomosynthesis. The absolute star of the show here is the PMMA Phantom. It's basically a block of plastic that acts just like breast tissue, which lets us take the same measurement over and over again. And the key number to remember is this. 45 millimeters of PMMA is the universal standard for a typical 50 to 55 millimeter compressed breast. Of course, you can have the most perfect image in the world, but it's totally useless if you're looking at it on a crappy monitor. For the radiologist's main screen, the specs are no joke. You need at least 5 megapixels, it has to be super bright, perfectly calibrated, and the room itself needs to be really, really dark. So, out of all the checks you can do, what's the one thing that absolutely has to be done every single day, no excuses? It's checking the SNPT test pattern. It's a quick visual check that confirms the monitor can show you the full range of grays you need to see to spot something subtle. And as technology moves forward, so does our QC. For 3D mammography, tomosynthesis, you have to add a whole other layer of tests. We now have to check that the tube's motion is geometrically perfect, check the resolution between the image slices, and look for artifacts that only show up in these 3D reconstructions. And that brings us right back to where we started. This quote just says it all, doesn't it? Quality assurance isn't about paperwork or ticking boxes on a form. It's an active, clinical process. It's the daily promise that all of this complicated physics is actually working the way it's supposed to. So I'll leave you with this thought. For anyone who works in this field, this is the question that QA is designed to answer every single morning before the first patient walks in the door. Is your system's physics working today? Because it absolutely has to be.